Today we're going to talk about section 4.4, radical functions. We're going to learn how to restrict the domain of the function that's not one-to-one so that its inverse is a function. And we're going to learn how to graph radical functions using some things we already know. So first of all, what is a radical function? Well, a radical function is just a function that contains at least one variable can't write today. One variable in the radicand. Now, it helps if we remember what that means. Okay, this is a radical, square root. You can also have a cube root, or a fourth root, or a fifth root, and so on and so forth. And if you have a variable in there, any one of these would be radical functions. Now, the simplest radical function is f of x equals the square root of x. What does this look like on a graph? Well, we have to have a limit. We're only graphing in the real plane. So we have to have x greater than or equal to 0 because we don't want complex numbers. And our graph looks like this. Now, if you remember this graph and you remember all our translation rules, then graphing the other ones should be not too difficult at all. Our y-intercept here is obviously at 0, 0. Our x-intercept also, we only have 1, and it's at 0, 0. So we have our domain here, and our y-intercept and our x-intercept. So let's look at a couple. If I ask you to find the domain and the x and y intercepts, for this function, well, we look at it and we say this is a radical, and we're only dealing with real numbers right now, so we know that this interior part here has to be greater than or equal to 0, or else we're going to end up with imaginary numbers, which we don't want. So we subtract 64 from both sides. This is just algebra solving inequalities. And we get negative x is greater than or equal to negative 64. So we divide by negative 1. Now remember, when you divide by a negative and you're solving an inequality, you have to flip the inequality around. So our domain is x such that x is less than or equal to 64. Now, what are our x and y intercepts? Well, for an x-intercept, remember, that's where it crosses the x-axis, so y equals 0. And for our y-intercept, that's where it crosses the y-axis, so x equals 0. So the y-intercept is easy. We just come over here, put in 0, and we get 64 minus 0, which is just 64. Take the square root, and we get 8. Then, for our x-intercept, we want to know when this function value here is equal to 0. Well, we've already pretty much solved that. If we have this equation here, we said that x has to be, if we want it equal to 0, then that just means x has to be equal to 64. So we have our domain, our x-intercept, and our y-intercept. We have to limit the domain in these to make sure we stay in the real plane. Now what if we have one that's a little more complicated and we want to find its domain? Well, how about this one? We have the square root of x squared plus 4x plus 3. If I want to know what the domain is, then I still have where I have to take the interior of the radicand and I want it to be greater than or equal to 0. So this factors nicely to x plus 3 times x plus 1. That's greater than or equal to 0. Well, you might recall from Algebra 2 that what this means is that x plus 3 has to be greater than or equal to 0, and x plus 1 has to be greater than or equal to 0. You've got to have them both positive, or you've got to have them both negative so that the product will be positive. So we look at that, and we solve here. So we've got x has to be greater than or equal to negative 3, and x has to be greater than or equal to negative 1. Well, if we take these and we just use the x is greater than or equal to negative 1, that satisfies both of those because we want both of them to be true. If it's greater than or equal to negative 1, it's already greater than or equal to negative 3. But if it's only greater than or equal to negative 3, it may not necessarily solve this one. Over here, we'll have x less than or equal to negative 3 and x less than or equal to negative 1. Well, which one solves it all here? Just the x less than or equal to negative 3 solves it here. Because if we have x less than or equal to negative 3, it's already less than or equal to negative 1, so this takes care of both of them. So what does this mean? This means for our domain that we have x such that x is greater than or equal to negative 1, or x is less than or equal to negative 3. Either one of those cases will satisfy the domain and make it so that this will be a real number. Now, what about our x-intercepts and our y-intercepts? Well, same thing. X-intercept, y is equal to 0, so we've already almost solved that. So we have two of those. You can look here at this equation here and see that you've got negative 3, 0 and negative 1, 0 are our x-intercepts. And for our y-intercept, plug in x equals 0 here, and we end up with the square root of 3. So here's our domain and our intercepts for this one. This, make sure you review this. This is something you learned in Algebra 2, so make sure you still got a handle on those things. Now, one thing you need to remember, for a relation to be a function, you've got to have no repeated x values in your ordered pairs. Now, for it to be one-to-one, we had to have no repeated y values. Remember, for the function, we did the vertical line test, and for the one-to-one, we did the horizontal line test. Now, for a function to have an inverse that is a function, the original function has to be one-to-one. If you think about this, it makes sense. If I have a function here and it doesn't pass the horizontal line test, then when I take it and I take that y equals x line and reflect it over the y equals x, then I'm going to end up with something that's not going to pass the vertical line test, which means it won't be a function. So I've got to have a one-to-one function for it to have a inverse that is a function as well. So let's see. Let's go back to black here. So let's see if we can figure out if a function's inverse is going to be a function. It'll be a relation because it'll be a set of ordered pairs, but will it be a function? And then we'll figure out what the rule is for the relation, or for the inverse. So if we have this function, f of x is 8x cubed minus 12x squared plus 6x minus 1. The first thing we want to know is this 1-to-1? If I plug in x values, am I always going to get a different y value no matter what I plug in? And the answer to this is yes. This function is 1-to-1. If I plug in -1, I'm going to get something different than if I plug in +1, because I've got these cubic function and this linear part here that are going to take the negatives into account. So this function is 1-to-1. Every x has a unique y. So we know that the inverse, written like this, remember, is a function. So now we just have to figure out what it is. Well, let's give ourselves some room here. If you remember, the way we do an inverse is we have to switch our x's and y's and then solve for y again, because what we're doing is we're taking a reflection over the line y equals x. So we have y equals 8x cubed minus 12x squared plus 6x minus 1. So to find our inverse, we switch the x and the y. 8y cubed minus 12y squared plus 6y minus 1. Now, this function here, if we want to solve for y, we're going to have to factor this down. And you're going to have to use your synthetic division and get it all factored down. But it factors to 2y minus 1 cubed. Go ahead and make sure that you use your synthetic division and remember how to factor this. We covered this last chapter, so you need to make sure you still know how to do this. Once you get it factored down, then we take the cube root of both sides. And then add 1 to both sides. And then we're going to end up dividing by 2. And so this is our inverse function rule. Now, do we have to limit the domain on this one? Well, there's no variables in the bottom of the fraction, so that's taken care of. This is a cube root. You can take a cube root of a negative number, so that's taken care of, and it's not a problem at all. So our domain for both this function, which is a polynomial, so we know its domain is all real numbers, and for this one here, it can both be all real numbers. Now, what if it's not quite that simple? What if we have a function like this? So we ask ourselves, is this 1-to-1? Well, is it? No, it's not. Because if I plug in a 1 here, I'm going to get the same answer as if I plug in a -1, because all I have is this x squared. So this function is not 1-to-1. You'll notice from our formula that we learned with parabolas that our vertex is at 0, -1. And we have this. And if we plug in, let's say x equals 1, then we're going to get plus and minus a half. We're going to get minus a half, rather. And we'll end up like something like this. And there's our graph. You notice it would not pass a horizontal line test. This is not 1-to-1. So what does that mean about its inverse? Well, what it means is the inverse is not going to be a function. It'll still be a relation, but it won't be a function. So we'll have to limit its domain so that we can have a function. So we look at this and we say to ourselves, well, if I limit this to just this part here, where I'm just dealing with this positive part, then I'm going to have a one-to-one function because I've limited my domain so that it's just one-to-one. And then I can find an inverse for just that part. All right, so if we go back, we've got f of x is 1/2 x squared minus 1. And we said we wanted to limit it to x greater than or equal to 0. So we want to find our inverse now. So we switch. We've got y is 1/2 x squared minus 1. And we switch those so that we have x is 1/2 y squared minus 1. So now we just solve for y, add 1 to both sides, multiply by 2, and then take the square root. Now, we're looking at for x greater than or equal to 0, so we only need to worry about the positive part for our function. But for our general rule for the whole thing, we'll still have this. So if we were just writing the rule for the inverse for the whole thing without the limit, we would have our inverse is plus or minus the square root of 2 times x plus 1. If we were writing it with this limit, we would have a function inverse, and it would only be the positive square root. Because then we have just this portion here of the function, and then we have our inverse, which looks something like this. Now, if you notice here, we've got a square root, so we've got to limit our domain for, this one is for the domain for f. If we have a square root here, we need to limit our domain for the inverse as well, because we can't have negatives in here. So what's going to make this one negative? Well, anything less than -1. So we need x greater than or equal to -1, otherwise this will be negative and we'll end up with complex numbers. We're just graphing in the real plane, so we don't need those complex numbers. So we limit our domain of the function and the inverse both. The function limit gives us a function that's an inverse, and the inverse limit just gives us what's going to work for this inverse. Make sure you've read section 4.4 and taken notes on it. We'll check the notes in the next class.